Hi everyone, my name is Bing Zhuo from Technical University of Munich. Today I'm going to introduce a set-based approach for synthesizing controllers, which can be used to enforce omega regular properties over uncertain linear control system. Nowadays, there is increasing demand in synthesizing correct by construction controllers over high-level logical properties in many safety critical applications like autonomous vehicle, delivery drones, traffic networks, and so on. In this paper, we focus on a particular type of high-level logical properties, namely omega regular properties. This kind of properties is a superset for those properties expressed by linear temporal logic formula. So we know that many specification in robotic application can be written by linear temporal logic formula. For the ease of presentation, I'm going to use the case study to provide you with an example how would an omega regular property look like. So in the case study, we focus on a linear dynamic of the buck converter with a dynamic like this, in which X1 denotes the output voltage of the circuit and X2 denotes the difference between the current in the circuit and the reference current. And we have the disturbances like this. And it is desired that if X1 has been to the region 221 to 222, then X1 should not enter the region 218 to 219 afterwards. So there's logic behind that. And we also have some additional requirement over X1 and X2. Some property like this can be characterized by a deterministic street automata. So this is actually also an example for omega regular properties. And we usually use DSA to model such property. And DSA look like this. I will come back to the definition of DSA in the next slide. And what I want to convey in this slide is that we focus on systematically synthesize a controller over linear system like this, and enforcing the property like this. So, and this may be a little bit challenge when you try to solve this problem using traditional control methods. So this is the motivation. So concretely, all the omega regular properties can be modeled by DSA like this. And the formal definition is on the right-hand side, in which capital Q denotes the finite state set. Q0 is the initial state. Capital Pi contains a finite set of alphabets. So within the alphabet, there is some atomic propositions over the transition within this DSA. The evolution of the DSA is driven by the evolution of the state of the system using the labeling function. And this is an example about the interplay between the physical system and the DSA. Suppose that the current state of the DSA is Q0 and the current state of the system belongs to R1. Then Q1 would be the new state of the DSA because the labeling function map X to P1 and there's a transition from Q0 to Q1 with P1. So this is one of the possible transition of the DSA, and the small d characterize the set of all feasible transitions. Finally, whether the desired omega regular properties modeled by these DSAs is satisfied can be captured by so-called the acceptance condition of the DSA. So basically, the acceptance condition contains some set E, F, which are subset of the state set Q. And if the desired omega regular property represented by this DSA is fulfilled, which means that there exists a state one of the DSA, which is a sequence of state of the DSA. If there exists a run such that for all the state within ER and FR, either the state in ER are visited only finitely many times, or the state within FR are visited infinitely many times. So if one of these conditions is fulfilled, then we say that the corresponding omega regular properties is fulfilled. And formally, we focus on uncertain linear system with compact input and disturbance set of the form of polytope. And we focus on synthesizing controller enforcing desired properties modeled by DSA. So this is the DSA. And here is the acceptance condition of the DSA, as I have mentioned in the previous slide. So in this paper, we focus on a subset of the possible controller that can be used to enforce this property. We try to propose a controller that prevents the state in ER from being reached so that the state in ER are only visited finitely many times. And we design such a controller by computing so-called hybrid control invariant set over the product system between S and A. And here's the definition of the product system. The product system has the hybrid state set in which there is some element like this. So the hybrid state contains one element from the continuous state set of the system and two discrete states comes from the state set of the DSA. So the discrete state here denotes one of the beginning of one of the possible transition in the DSA and the end of this transition. So there is a transition from Q0 to Q0. So we have a state like this. We can construct the initial state set of the product system similarly, but we only focus on those states within the initial state of the physical system. The input and disturbance set of the product system are the same of those of the physical system. And we construct the transition function of the product system by coupling the dynamic of the physical system and the DSA. So here's an example. If there exists a U and W that can take the system from X to X1, and the labeling function map X1 to P1, then the next state of Q0, Q0X will be Q0, Q1, X1. So this is how we couple the dynamic of the S and the DSAA. Again, suppose that there exists a U1 and W1 that can bring the system from X1 to X2, and X2 is mapped to P3 according to the labeling function. Then this will be the next state because there is a transition from Q1 to Q2 using P3. We want to enforce the desired omega regular property by preventing the state within ER from being reached. And from the product system perspective, we do not want those hybrid states that contain the state within E to be reached. So this is how we translate the synthesis problem to the perspective of the product system. And how could we do that? We do it by computing a so-called hybrid control invariant set, which is a subset of the hybrid set underbar X minus underbar E, such that for all the hybrid states within the HCI set, there exists a controller such that the system will still within the this set at the next time instant, regardless of all possible disturbances. And in the remaining of the talk, I will discuss how to synthesize such a set. So here is the iteration that can be used to compute the maximal HCI set. You may notice that this is similar to those procedures for computing control invariant set for continuous system. So the good news is, if we perform a similar process over the hybrid state set, we may be able to obtain a controller to enforce those omega regular properties, not only simple invariance property. So both P here denotes the computation of the one-step backward projection of the set II underbar. So here is an example. We consider the aggregation of hybrid state like this. So here, X1 denotes all those states that can be mapped to P1, so that the transition from Q0 to Q1 can happen. And we denote by I underbar 0, Q0, Q1. as the aggregation of this continuous state. To compute the one-step backward projection of this hybrid state, we are actually computing all the hybrid steps that can reach the hybrid state here within one step. So to do this, we copy Q0 and we compute all those continuous states that can reach a smaller region with respect to I0, Q0, Q1 within one step. So here the deflation is related to the disturbance set. And finally, we see all the possible transitions that can reach Q0 within one step. And in this case, you can only find Q0 because you can only reach Q0 from Q0. And this is how we compute the one-step backward projection regarding these hybrid states. And we keep computing the intersection here and check the stopping criteria here. So the checking the stopping criteria here means that we need to check whether for all the Q prime within the state set of the DS8, the corresponding aggregation of continuous state are the same. So if at some point for all QQ prime within capital Q, the corresponding underbar II QQ prime and the one in the step I plus one are the same, then the procedure here terminates and we obtain the corresponding hybrid control invariant set. So this is an example for the case study. So we do not want Q2 to be reached. We start from the initial hybrid state set and we compute the corresponding one-step backward projection considering the linear dynamic and the dynamic of the DSA. And then we compute the intersection. So here, the intersection G contains two parts, namely the intersection between A and B and the intersection between A and B. So this is an example for how we compute the intersection here, and we keep doing this until the stopping criteria is fulfilled, and then we obtain the HCI set. And for this iteration process, we guarantee that we can obtain the maxima HCI set when I goes to infinity, given that I0 is compact. But the problem here is we do not have any guarantee for general case that the procedure here can be terminated within a finite number of steps. So this problem motivates us to propose an alternative iteration process, which can be used to compute an inner approximation of the maxima HCI set. But for this iteration process, we have guaranteed that it can be terminated within a finite number of steps. So here is the original iteration process as I've mentioned just now. To compute the inner approximation of the maxima HCI set, we only need to slightly revise the iteration process here by selecting a parameter epsilon. So quite quickly, with this epsilon, we compute the one-step backward projection by considering a larger disturbance set. And we also revise the stopping criteria by considering an inclusion relation instead of to check whether they are the same. So you may already notice that if you select epsilon equal to 0, this process exactly recover the original iteration process that can be used to compute the maximum HCI set. But here we guarantee that if you select an epsilon which is larger than 0, then the iteration process here is finitely terminable. And if you terminate the process, you can construct the HCI set in this way. Here's the case study. We select epsilon equals to 0.01 and we terminate the process within 5 iterations. And to show the effectiveness of the controller, we randomly select 10 different initial states and simulate the system. And we see that all the desired properties are actually respected. So concretely, if the evolution of X1 has been to the region 221 to 222, it will become red, and we cannot see any evolution within the region 218 to 219. And also both of these regions are respected according to the evolution so that the desired property can be enforced by our HCI-based controller. To summarize, here we focus on enforcing omega regular properties for linear system affected by bounded disturbances. And we reduce the synthesis problem here to computing so-called hybrid control invariant set using a set-based approach. Also, we propose an alternative iteration process so that with which you can compute an approximation of the maximal HCI set, and we guarantee that you can obtain such approximation within a finite number of iterations. In the future, we are planning to reduce the conservativeness of our proposed approach. As you may already notice, we are only considering a subset of all feasible controllers that can be used to enforce the design omega regular property. Namely, we try to let the second condition here hold by preventing the state from being reached. So therefore, we are interested in how to synthesize controller that allow ER to be reached finitely many times, which is larger than zero, of course. And we are also interested in those controllers that can be used to enforce FR to be reached infinitely many times, so that even though ER is also being reached for infinite many times, it doesn't matter because we only need one of these conditions to be respected. And this brings to the end of my talk today. Thank you very much for your attention. And if you have any question, please feel free to contact me. Thank you.